It's my pleasure to introduce Kevin Jamieson today. Kevin's made some really important contributions in areas of active learning and stochastic optimization for devising sequential data collection strategies. And Kevin's actually one of our own. He was a UW undergrad alum, and then he went on to the other UW, University of Wisconsin-Madison, to do his PhD with Rob Nowak. And he's now a postdoc with Ben Recht at Berkeley. And today he's going to be giving a talk on efficient scalable algorithms for adaptive data collection. So, thank you.
Thanks, Emily. It's a pleasure to be here. So in the last decade or so, we've seen a huge number of recent advances in object recognition, image classification, and translation. And a lot of these advances are thanks to these very modern networks, or modern classifiers, known as deep networks. And these models are very, very expressive. They can learn just about anything, and the reason why they work so well is that they're learning the training set very well. And so that means that they have to have an enormous training set to actually learn effectively. And being in the era of big data, this isn't such a problem. The trouble is that we need labeled data to actually train these classifiers and these different predictors. And these labels have to be given by humans. And mostly, humans like to be paid for their work. And so while we have things like ImageNet and CIFAR, these larger data sets for training image classifiers and translation data sets, the question is, how do we train the next problem? So if you wanted to train something for a home intrusion system, how do you tell the difference between intruder and mailman versus the bush that comes into the frame every once in a while? And how do we do this effectively so you don't need the kind of image sizes of ImageNet? The second challenge with these very deep networks and these very representative models is that they take an enormous amount of wall clock time to train. So something like a translation model can take months to train from beginning to end. So these two challenges of needing label efficiencies, train these same quality of models with less labeled data, and wall clock time to train these things are two issues that I'm trying to address in some of my research. And so to give you an example of what I mean by label efficient, training with less labels to teach these classifiers different things, consider all the images on Google Image Search that can be classified down into airplane, automobile, or bird. Okay? How a typical data set would be collected is we have some feature representations for each one of these images. Pick your favorite features. And then when we have a data set like ImageNet or CIFAR, they're collecting a representative data set, which is a random sample of images. So they just collect a random sample of these images on Google Image Search, and then they ask people for the labels of this representative sample. What they do next is we now learn a classifier that says gets 0 training error on the training set. But the problem is that this classifier has a lot of wiggle room. It can be moved around a lot, and these black dots are the images that we didn't collect labels for. And because we can wiggle this classifier around, this means it has additional error. This is what translates into the error of this classifier because we didn't know how to recognize those black images. An alternative way of training a classifier would be an adaptive label assignment. The way this would work is you might start by you might start with one label, like a blue sample, just randomly sampled, and then maybe you get another random sample at some other point. But then maybe this for the third sample, you want to somehow sample something that's most uncertain. So perhaps something at the midpoint between these two labels. We're most uncertain about this label, and maybe we repeat this process. We're always collecting labels that we're sort of most uncertain about and might be most informative for creating a classifier. And the point here is that we're collecting these labels in the pursuit of actually building a classifier at the end of the day. And so when we do build this classifier and move it around, it has less wiggle room. Okay? And less wiggle room, again, is less error. So in a learning sense, we are from VC theory and different pack bounds, we know that for a random sample data set, things coming IID from some data set, the representative data set, as the size of the data set increases, we know that the error of this classifier goes down. Like a traditional 1/squared event rate or something like this. The promise of adaptive sampling is to be able to find a classifier with the same number of labels and get a much less error classifier because you're collecting these labels in an adaptive way. Or said another way, the hope is to achieve the same level of error with this classifier with far fewer labels. Unfortunately, this procedure I just went through on the last slide, this uncertainty sampling, I think rather arbitrary. There's many other ways that I could have collected this data in the pursuit of building this classifier. And with these different options to collect data comes trade-offs. Trade-offs in computational complexity, in reliability, robustness, which matter in modern real-time environments. And so the point is even if you're convinced that you want to be adaptive, that you want to collect data adaptively to get these gains, it's not clear what the trade-offs are and how to be adaptive. To give you a case study and the kind of trade-offs that we have to address, consider this Drosophila RNA interference study. So this was done at Wisconsin a number of years ago. And the biology is not too important to follow, but the basics here are they start with 13,000 genes for this Drosophila. And what they do is they knock out an individual gene, or they hope to. It's sometimes a little more messy. But for the purpose of this conversation, they knock out a single gene, and then they replicate this strain. And then they infect it with a fluorescing infecting virus. Okay? So the point here is that if this gene was very important for inhibiting virus replication, then what will happen is that if it's knocked out, you'll get a lot of fluorescing, a lot of virus. And if it was not important, you won't get a lot of fluorescence. Okay. It's a very noisy process, so that they repeat each measurement many, many times. So what this study did, this Wisconsin study, they came up with an adaptive protocol because measuring each gene many, many times was too much. So what they did is they measured all 13,000 genes twice, applied a z-test, simple test for significance. Then they ruled out enough genes to be just about 1,000 genes. Then they measured each one of the genes 12 times to rule out, applied a z-test and got it down to about 100 genes. Okay? The procedure was much more sample efficient than measuring each gene 12 times, of course. And because of the sample efficiency, consequently, other labs wanted to replicate this study. So these were papers that were published at Cell and Nature, these major biology journals. And then, so the initial authors saw this, went back, looked at these papers that were supposed to be replicating this study, and only found 3 to 15% agreement between all 4 studies. Okay? This is kind of a nightmare scenario. This is where someone comes up with an adaptive protocol, it gets popularized and taken up by the literature, and then only later do we figure out that we were just looking at noise the whole time and not looking at true discoveries. And so what I'm trying to point out here is that we need to be careful. And so in my work, what I try to do is come up with sample efficient and practical strategies, but also reliable strategies for adaptive data collection. And when I say reliable, I mean things like guarantees, theorems that say, with probability 1 minus delta, or with probability 0.95, you'll get the same genes over and over, or a large agreement between the different genes different times. Over my PhD, I started with preference learning. And this is this problem where we have problems like I have n beers, maybe 100 beers on tap, and I'm going to try to make a recommendation to you by giving you little pairwise comparisons. I'll show you a shot glass of beer, another shot glass, and say, what do you prefer, A or B? And then send you another one, B or C, C or D, E or F. This goes on for a while, and I find your preferences over these beers. Okay, so what we can do is we can characterize, write down a model for this, characterize an algorithm, and an upper bound, and an information theoretic lower bound, and try to get this to work. And so consequently, it did work pretty well, and so I turned it into an iPhone app. So it works, and it was eventually acquired by a company in Chicago that does development now, so don't blame me if you get bad recommendations. So that was over a discrete space of options, like n beers, but you can also talk about a continuous space, doing optimization over, say, prescription lenses. You have your prescription lenses, you pick one, pick another one, better or worse, always going downhill. We can, in the space of convex functions, we can model this as a stochastic derivative-free optimization problem. And so I characterized some of the first rates for dimensional dependence in this setting from information theoretic lower bounds, and again, also upper bounds with an algorithm. At the University of Wisconsin, I was working with psychologists. They were interested in this problem of if you're given say 250 emotional words, and then you're given 3 of these words, say fear, joy, or love, they would say, is joy more similar to fear or love? And they'd want to find a Euclidean embedding such that the distances in Euclidean space were most aligned with these triplet comparisons, these distances comparisons, which is more similar to which. And so what they do is they bring in a dozen or so people at a time and collect this data over the course of a number of days. And then we have adaptive algorithms for this. Later in my work, in the last few years, I started getting interested in the fundamental limits of adaptive sampling. And so multi-armed bandits became a nice framework to study these limitations and how well can we actually do with adaptive sampling. What are the limits here? And consequently, one of the applications I worked in was with the New Yorker, which I'll get to in a moment. But this was in a web environment with tens of thousands of individuals contributing to a specific task. And so as my work has gone from working with individuals to working with tens of thousands, the way I collect data has had to change. And consequently, the way I had to collect data was in these web-based environments. And so I had to develop this machine learning system called Next. So what Next is it's essentially a system that makes it easy to take an adaptive sampling learning algorithm from an algorithm box in a paper into a real deployed system on the internet, say Amazon Web Services, EC2, these sorts of things. And who it's for is ML researchers like myself for our NIPS papers and things like this. But then it's also for experimentalists, like those psychologists. Before, they were bringing people into a lab a dozen at a time, and it was taking days and days to collect data. And some poor grad student had to be there the entire time. Now they get the same data with adaptive algorithms in an afternoon. And then finally, we had an intern go to American Family Insurance who then implemented it in their stack, and it's now running in production to fill in missing claims information from these expert data people. And so over the course of my career that I've had, these different applications, the different code that's been developed, of course, because Next is a system to deploy active learning algorithms, consequently, all my stuff is implemented in Next and available, of course, open source on GitHub. So you can go and use it, or you can implement your own to improve these algorithms. Working with Next, building this machine learning system actually got me very interested in distributed computation and also wall clock time. A lot of work that I was doing up until this point was interested in characterizing the sample complexity of different problems. How many questions do I need to ask in order to solve some problem? But also there's other issues of computation. How much work, how many resources do I need to allocate in order to complete some task? And so consequently, the last 4 or 5 months, I've been at Google up until about a month ago, where I use these same sort of techniques for adaptive sampling applied to resource allocation for doing hyperparameter tuning for training deep networks. So I don't have time to talk about everything, but I'm going to talk about these. I'm going to deep dive on these 2 topics today, and then finish up with some future work and some ongoing problems in active learning and systems biology and robotics. OK. So diving into the first task, the New Yorker magazine is an institution. They have this cartoon caption contest. And what this is they have a cartoon in the back of a magazine, and they have no caption on this cartoon. What they do is they invite their readers to submit captions, and they get about 5,000 of them a week. Okay, this happens every week. This is the cartoon of Trump's inauguration, and so the winner picks these winners. So it's 3rd place, 2nd place, and 1st place. Okay, and where did these come from? They were picked by this guy, Bob Mankoff. He's the cartoon editor. We got hooked up with him because he was talking to some psychologists at the University of Wisconsin, and he was lamenting about the fact that he had to look at these 5,000 captions each week and decide which of these 3 funny ones to actually publish. And so what he wanted to do was crowdsource this. And because the psychologist had worked with us before in the triplet problem, the metric learning problem, she knew that we did crowdsourcing and that we could work with him to get this done. So what we can do is model this as a so-called best arm identification in multi-armed bandits. I'll get into exactly what that means in a moment. But the idea here is we're going to crowdsource the contest with these volunteers that come to the website to figure out which captions are the funniest. And of course, this is hosted on Next, this machine learning system that's used to this through an API. They just contact us, or you can go directly to the site, or newyorker.com/cartoon/vote. What people see is they see a cartoon, they see a caption, they rate unfunny or funny, unfunny or funny, and unfunny or funny. Okay? The task here is what is the caption that we show next? Once you've clicked funny or unfunny, what do we show next in order to figure out what is the funniest caption out of all 5,000? One strategy would be a non-adaptive approach. This would just say when someone shows up, I choose one of the 5,000 uniformly at random, so each of the 5,000 gets about the same number of votes, and then I pick the empirical best at the end of the day. Okay, reasonable strategy. Or you could do something adaptive. In adaptive, I mean stop showing captions that have no chance of winning. So once everything's got some number of votes, stop showing the ones that can't possibly win, so you can get more votes on the best ones and get a higher statistical significance. To give you some indication that this is actually doing something and working, when we compare the adaptive algorithm I'm going to describe in a moment to the non-adaptive, this uniform allocation, we can see that we can identify funny captions 45 times faster. And so if this is, if you were paying for this data, it's not bad to be able to identify the funniest caption 5 times with a fifth of the data. So of course, this is just cartoons and captions. But what I want to emphasize here is that the caption contest is really a model for other domains. Just like with the gene experiment, you measure one gene at a time, and you can't do dozens at a time. You're doing one at a time, and they each require a measurement. And so what we can do is use this as a platform in order to study these other problems in these other domains. The difference between this and, say, a biology experiment is that the caption contest is free. It's rapid turnaround. I can change the algorithm from week to week, and with minimal risk. Nothing happens if it goes wrong. So we've been doing this about 60 weeks now. We get 1 million labels a week from about 20,000 unique people. And to put in that context, it's about $20,000 a week if we were to pay for this on Mechanical Turk, and allows us to study all sorts of different phenomena leading to a number of publications. So the problem defined is that each time when someone shows up to the site, the algorithm chooses some caption I from the N, and then it observes some Bernoulli random variable, a coin flip, with the probability of being funny as equal to mu I. Okay? And then, of course, the objective is to identify the funniest caption, the argmax mu I, with, say, high probability, 0.99, using as few samples as possible. So the difficulty of this problem, or the setup is defined by, the algorithm is defined by the sampling rule, what do you sample at each time, and the stopping time. Okay, so what this looks like, what these kind of algorithms for this problem look like, is you have some n captions after some amount of time. Let's say you're doing uniform allocation for the moment. So everything gets some number of votes, and you get some average number of votes are funny. Now, because they have a finite number of votes for each caption, we have confidence intervals. And these confidence intervals act like 1 over the square root of the total number of votes you've received for each one of the captions. In addition to the number of votes, though, you also have this log n showing up in the numerator. We call this n captions, and this log n is this so-called union bound. And it's there so that to account for this spurious stochastic behavior, in the sense that if I have 5,000 coins, the probability that any one of them gets 10 heads in a row is very small, but the probability that at least one of them gets 10 heads in a row is actually very large. So this union bound accounts for that. And what it does is it makes sure that each one of the means, the true means, is enclosed in each one of these confidence intervals. So what happens if we were doing uniform allocation? You keep sampling each uniformly. The confidence intervals shrink. And eventually, we get to this point where one caption is poking its head above all the other captions, assuming there's a fixed gap. And we can make sure that that one actually is the best caption because there are all the confidence intervals enclose their true mean, and the lower confidence bound is above all the other upper confidence bounds. Okay? But of course, okay, and so we can easily characterize the sample complexity of this problem. If delta 2 is the gap between the best arm and the second best caption, this best caption and the second best caption, and delta I is the difference between the mean between the best caption and the ith best caption, then a simple manipulation of these quantities yields just setting these things equal to each other, essentially. For any uniform non-adaptive strategy, it's going to be n times the worst case inverse gap squared times log n. Okay, this is for non-adaptive. But of course, this is an extremely naive strategy because we oversampled these guys. All we need to do is get their upper confidence bounds below this blue line here, but we oversampled them, and so it's much less than that blue line. So the next less naive strategy you might do is say, well, stop sampling the ith caption as soon as its upper confidence bound is below any other caption's lower confidence bound. Okay? If you do that, you get this very simple difference where instead of having the max, n times the max, it's just the sum of the inverse gap squared. Okay? Again, times this log n. Rewriting these expressions on this slide, we have the non-adaptive and the successive elimination strategy that I just described. Put this in context, we know a lower bound was proven a great number of years ago. That's been improved over time, but this will suffice for our needs without the log n. Okay? So these both quantities have this log n factor, but we know this lower bound doesn't have this log n. And if you do, with a simple argument, you can say that any algorithm that's using these confidence intervals with this log n, this union bound in the numerator, and you use these confidence intervals to stop, this log n is going to have to show up in the stop in the n sample complexity. And for the kind of applications I'm interested in, where n is in the thousands, like 5,000 captions or 13,000 genes, log n is about 10. And these constants are actually quite small. I mean, I'm suppressing constants and log factors, but you'll have to trust me that the log n factor is actually playing a role in here, and you'll see some simulations to that effect in a moment. So what I'm going to propose today is an algorithm that gets away from these log n, these wasteful union bounds. The idea is to have confidence intervals that don't perform this union bound, and then also propose a novel stopping time. So how this algorithm works, it's an upper confidence bound based algorithm. And so the rule at any given time is you have some u hat I t I. So this is the average number of times the ith caption was rated as funny after being shown ti times. And then we have something that looks a lot like that confidence interval on the last slide. We have this familiar 1 over square root of ti, but then we have this log ti factor, which I'll explain in a moment. And then we also have no log n. And the no log n factor is the big issue here, because what it means is that if I draw these confidence intervals down here, it means that the true mean is actually not enclosed in one of these confidence intervals with high probability. Okay? So this is unlike those other algorithms in that we have these we're not making this into an event-based analysis and then doing a deterministic thing that holds high probability. What we're actually saying is that these are just an algorithm. And at each time, we're going to sample the caption that has the highest upper confidence bound. If we do this, it has the effect of minimizing the maximum upper confidence bound. And eventually, if you keep sampling, according to this rule, you'll have one caption that pokes its head above all the rest. And consequently, since you're sampling according to this rule, it will be sampled more than all the other captions combined eventually. So in fact, that's exactly what our sampling rule does. So it'll be sampling. This is a little video. And on the bottom here is the proportion of times each caption is being shown. And so eventually, one caption is being shown way more than the other ones. And we actually use this exactly as a stopping time. When there exists some caption I that's been shown more times than all the other captions combined, stop. And so if you go through this analysis of this stopping time and these sampling rules, you can actually show that this achieves the lower bound that I had in the previous slide. And this is actually the first practical algorithm. This is the first practical algorithm, but it's not the first algorithm to actually achieve the sample complexity result. There had existed analyses before that had gotten the sample complexity, but with a large constant. Essentially, they were existence proofs because you couldn't actually implement them. And the reason I can say that is because one of them was mine. And so the novelty of this was actually proving a finite sample form, the law of the iterative logarithm. That's where that log t showed up. And basically making the constant small enough to make it practically useful. And then also this idea, this principle of don't pay for the union bound, just don't pay for it and hope that everything works out, and then come up with some clever stopping time and prove that it's actually correct and some given sample complexity. So real quick, just in simulation with just 1,000 alternatives, so 1,000 captions, let's say, in the situation where the sum of the inverse gap squared is much, much smaller than n times the worst case inverse gap, we have predictably lower is better, that successive elimination dominates non-adaptive, but then low UCB improves over that. In the situation when they're equal, say in the one spike model, we have that successive elimination is exactly on top of non-adaptive as predicted by the theory, but low UCB, by removing this log factor, gets this additional improvement. So I opened this talk by saying that I'm going to talk about reducing sample complexities of these very complicated models like deep learning. But then I talked about this seemingly very simple problem, like multi-arm bandits. And the connection here is that the accuracy of a classification model is analogous to the funniness of a caption. And if we look at the standard active learning algorithms for binary classification, say, all the theoretically justified algorithms, when we reduce them to the best arm identification problem, this caption problem, we're trying to find the best, which we can do, all these optimal algorithms actually reduce exactly to algorithms that look exactly like successive elimination. Exactly this algorithm that has these union bounds and these wasteful factors that make it suboptimal. And this is interesting because many of these algorithms, these theoretically justified algorithms, don't work very well in practice. When you actually go to implement them, you'll see that non-adaptive sampling and successive elimination, or these style algorithms, are right on top of each other for these more structured problems. So consequently, in recent work, I've tried to build up what we've learned from LILUCB, these algorithms I described in the previous few slides, to more structured settings, or more combinatorial sets. And while it's still baby steps, we're still trying to increase our library of complex functions and sets to start to look like more binary classification problems that we'd like to get to. And so we have proposing algorithms to do just that. This is recent work that's submitted to COLT. So next, what I'd like to talk about is the enormous amount of wall clock time that's used to train these deep learning models. This is the second challenge with applying these very state-of-the-art models. So these modern networks, these deep learning networks, they have many, many hyperparameters to train or tune. And what I mean by that is if we take even a simple network, like this ResNet model of a couple years ago, that just has 4 stages for ImageNet. And at each stage, it has some number of layers, some number of filters, the size of the convolution, and this repeats through a number of stages. And all of these numbers need to be picked and chosen by the practitioner, and they have a real effect on the quality of the generalization of this network. How does it perform on future data? And the only way to pick these is through training the model and seeing how they perform. And of course, because this is non-convex optimization, something like a neural network, we have that the batch size and the learning rate, how it changes over time, actually has a real impact on the end performance, because you can get stuck in these local minima, even though the objective function has not changed. We also have other choices like the slope of the nonlinearity. This is a real hyperparameter that comes up, and it's not clear at all how to choose this thing. And then also we have things like data augmentation. Are you going to use patches, rotations, translations? How are you going to do these different augmentations to train your network? And all these things are just different things you need to choose to be able to tune anything. And so how we've done this in the past with something like Lasso or something like this with a couple hyperparameters where we can train something very quickly is we'll pick some setting. We'll start the optimization, go to a cup of coffee, come back. It's done. Choose the next one. Go get another cup of coffee, come back, and just repeat this sequential procedure of choosing one after the other, getting a validation there, and using that to guide the search of where to train next or what to choose next. Unfortunately, like I mentioned before, these networks, these modern networks, can take an enormous amount of time to train. And so if it takes a week to train one of these networks, you can't be hand-tuning these in one, as a very simple sequential fashion, one after the other. And so consequently, it's pretty clear that we need to have some sort of parallelism going on here. Right? We need to have K workers working at a time, trying out different parameter settings, and trying to find the right one that works. So if it takes a week to train a model, we get a fully trained model in about a week. The problem, of course, is that K workers is not all that much, especially when you've got something like 16 hyperparameters. To just get 2 in each dimension would be something like 2 to the 16. Impossible. You don't have that many machines at your disposal. And so we need to do something. But how do we choose these more intelligently? There's methods like black box optimization, like Bayesian optimization, that's become very, very popular in the last several years. But these are very sequential models, sequential methods. And if I only have time for one evaluation like this, there's no room for adaptivity. And so in recent work, what we showed is actually that even if we use random search, when we have terrible priors over how these hyperparameters relate to each other, random search, this very naive method, is actually very competitive with these black box optimization problems when the number of evaluations you have access to is small relative to the dimension of the space. So if the number of hyperparameters is large and you only have, say, 50 evaluations or 100 evaluations, random search is actually not a bad strategy. And so the idea here is to use early stopping, training these networks in small bits and throwing configurations out that don't look very good in some adaptive way in order to see more configurations, have some hope of covering this space, this exponentially large space. And so this work actually started off as theoretical work, something called the infinite arm bandit problem. But as I realized it had a lot of practical implications, I've been to Google, went to Google Research the last several months to actually implement this, to actually train these networks, mostly because they have the computational resources, they have many workers, and they have the motivation, certainly, to speed this process up. So in a smaller problem, let's just look at 10 workers. What does this adaptive algorithm look like? So before jumping into the adaptive, let's look at the non-adaptive. What does it do? This is just you're drawing configurations at random, and you're training them to completion. So on the x-axis is the number of iterations. On the y-axis is the accuracy of the model. So it's a classification task. So if you're training, this is what you'll get at the end of the day. So that's after 31 hours. And the majority of these 10 workers have finished, and so this is my benchmark for when the majority have finished. That's sort of like when I want to have my model trained, because like I said, if it takes a month to train a network, I really want a fully trained model a month and a little bit. And so what does the adaptive algorithm look like? This is the non-adaptive, which just as soon as it finishes, it starts over in some non-synchronous or asynchronous way. The adaptive algorithm, all it does is it defines these thresholds. So define some constant eta, say eta is equal to 4. And then what it will do is we define these thresholds at eta squared, eta cubed, eta to the fourth, eta, etc. And now what we do is we look at all the configurations. We have all our workers asynchronously working. And the rule is as soon as one of these workers hits this threshold, it looks at all the other workers that have previously hit this threshold and the accuracy that their model got. And if it's in the best 1 over eta, the best 1 over eta fraction of those models, keep training. If not, stop yourself and reset with a new hyperparameter setting.
Sorry, what is the objective function? Is it training set accuracy, validation set accuracy, training sets something?
Yeah, so the objectives, so what's happening here is the network is being trained on the training set, and then we're trying to pick these hyperparameters based on the validation set.
So this is validation?
This is validation error, yeah. So the pattern here is these guys hit these threshold. We only keep the best 1 over eta and train for eta as long. Okay, so what's going to happen is is the culling process, and so only a small number are actually going to get through all of the thresholds. So if we just replay what the green that we had in the last, but we add on this new adaptive algorithm, just replaying this out in real time, same stopping time, we see there's 2 things to notice here. First, only 1 configuration finished, whereas the non-adaptive finished many, but all that work was actually front-loaded into these other configurations. So it looked at a lot more configurations, 92 versus 16, but it only trained 1 to completion. And it's sort of this bet. It's a bet that downsampling can help. It's like with sparsity. If the number of features you have is much larger than the number of examples you have, you better hope your solution is sparse, or else you're screwed. You're never going to be able to learn it. This problem, in terms of hyperparameter tuning, is sort of like if the number of hyperparameters you have is large relative to the number of total evaluations you have, you better hope that downsampling can help, or else you're screwed. You're never going to recover the space and learn it anyways. And so this is the paradigm that we're going to go forward with. Plotting the same data on a different way. So there's just data in a different way. Now the x-axis is wall clock time. And now the y-axis, the accuracy of the best model found in terms of validation error by this process over time. We can see that hyperband, this adaptive algorithm over time, is outperforming the non-adaptive. And these thin lines are just bootstrap samples to give you some idea of the randomness here, but nothing's super formal with this. Okay, so let's look at some bigger problems. So that was just 10 workers. If we look at 50 workers, so each with a K80 GPU on CIFAR10 again, with that same residual network I described in that first slide, 16 hyperparameters, you can look those offline. And we win, we do better, but of course this is a talk, so all the plots are going to look great. It also works with all convolutional networks, same algorithm, nothing changes. We start with an all convolutional network, and it also works. It also works for speech. So this is for an LSTM exercise where we have just 20 workers, but each worker is 125 machines, asynchronously training. And we get substantial gains here. And one of the reasons behind why we get substantial gains here is because with LSTMs, at least heuristically, they appear to be very finicky with their hyperparameters. And you're just waiting to get something into the basin of attraction or something good near the solution. And before you get there, you're just sort of stumbling around in the dark. So the difference between this work and, say, some of the other work, the excellent work that's out here that's been used for hyperparameter tuning over the last several years is general theoretical guarantees. And what I mean by that is that we don't need to make many assumptions on how these processes work. One way of doing this is what we can say. We can characterize the complexity, the theoretical properties of this algorithm through oracle inequalities. And what I mean by that is the algorithm doesn't need to know these things, but if we suppose that the validation curves of these curves as a function of the number of iterations converges something like 1 over the number of iterations to some power 1 over alpha, where alpha could be something like 1 or 2. And then we also have that if we sample configuration, randomly from this space, and that the probability of getting a configuration with an epsilon is scaling like epsilon to the beta, then through a Taylor series expansion, one can argue that beta is something like the intrinsic dimension of this problem. And what you have here is actually, when alpha and beta are unknown, is this breadth versus depth-based search problem, right? Because when you don't know these things, you don't know that whether you should look at a large number of configurations and train them for a small amount of time, or look at a small number of configurations and train them for a very long amount of time. Okay? And so some work that I've been doing in this area, so-called infinite arm bandit setting, has actually addressed this exact issue, and this is what led to the development of Hyperband. And what we can say is that if we applied the best non-adaptive algorithm, this algorithm will behave like something of 1 over the total number of iterations from all the configurations, to 1 over 1 plus alpha over beta, versus adaptive, the Hyperband algorithm. If we apply the same algorithm, but with a slight twist to hedge over that first stopping time, that first time that you start throwing things out, then the exponent goes to 1 over max over alpha beta. So if alpha and beta are something like 1 or 2, then this is a huge difference between sample complexities. We also have this guarantee by appealing to information theoretical bounds that these are theoretically minimax optimal. And so we know this algorithm is actually doing something reasonable. But one of the big benefits here is I've been talking about iterations and training these deep networks, but it's actually, you can talk about these things just in terms of general resources. So instead of iterations, I could have said, I'm going to allocate time, train everything for an hour, and then start throwing things out. Or I could be training something training some database, some Postgres database with all its different hyperparameters, with some representative query set. And now I'm just going to try different parameters out and start aggressively throwing things out based on this highly subsampled query set, the amount of time given to each configuration. And because the theory is so general, I don't need to worry about, I can apply this to any different domain. So in the last few minutes, I'm going to talk about some ongoing challenges in active learning that I'm interested in addition to, of course, the more combinatorial strategies that I was talking about with the more caption stuff of trying to get more combinatorial sets towards binary classification. But at the University of Wisconsin, I worked in a building, an interdisciplinary building called the Wisconsin Institute for Discovery. And what this meant was that I shared a window and a wall with a wet lab. And what I watched these people do all day is pipette. And they were very hard workers, and a lot of their time was spent pipetting. So one day, this machine the size of a large refrigerator showed up, and a couple months later, after it was set up, the amount of pipetting really dropped. And what this machine was, of course, was this automatic pipette, this robotic pipette machine. And what it allowed them to do is these high-throughput experiments with a minimum of labor. They just needed to fill up the materials for this machine, and then it would go and do these exhaustive high-throughput experiments with many replications. And as these machines become cheaper and more plentiful, startups have already started to allow you to buy time on these machines, just like you would buy time on Amazon Web Services. And as these sort of systems and these platforms start to resemble things like AWS and scale, the pace of discovery is really going to skyrocket, or at least have the potential to skyrocket. And while I've been talking a lot today about, it'd be nice if we could save, a fifth of dollars, or get the same answer with a tenth the amount of data, For these kind of things, the data collection will be becoming so rapid and so many experiments going on in parallel that wouldn't be nice to have these kind of algorithms. You need to have these automated algorithms because to have a human in the loop would just slow down the process. So consequently, in recent work and ongoing work, I'm working on combining the sample efficiencies of multi-armed bandits, the kind of methods that I've been talking about with the caption contest, with the strong reliability guarantees of FDR, false discovery rate, both in terms of over experiments. So if I'm doing a number of experiments that are totally separate, I want to maintain the false discovery rate on that, or with an existing experiment or existing gene study, a single experiment controlling FDR with this adaptive sample complexity. And also there's structure. These problems, like the multi-armed bandit problem, these caption contest problems, I was modeling these things as all the arms being independent, and one does not relate to another one. But in the real world, we have side information. And incorporating this side knowledge is one of the biggest problems in active learning. How do we robustly incorporate side information and structure into the problem without making it too brittle and not working in practice? And so working in these more structured settings and also in a robust setting is a topic of much interest to me. And I have some work towards this end already, trying to characterize the sample complexity of these kinds of problems. And a problem in particular I'm interested in is drug cocktail discovery. Basically, if I have n drugs, I want to pick the best k of them. And finally, robotics. Robotics, reinforcement learning. This is an enormous area of, it's been exploding over the last few years. We're learning a lot, and there's still a lot more to learn. But there's also a lot of active learning problems just in this field, particularly in learning from human demonstration. So suppose you wanted to train a self-driving car by machine learning. This is not always the case, but suppose you wanted to train a car by using machine learning, using human demonstrations. So how you might do this is the human gets into the car. There's sensors on this car that's observing state information, and the human goes and drives this car around, and then the robot then observes what the human is doing, and then learns a map from states to actions based on just what this human has been doing. Okay, this sort of teleoperating the robot sort of idea, learning from human demonstration. Then what happens is the robot then goes and practices its policy, meaning it drives on the road, self-drives, until, of course, the robot makes a mistake. Right? It runs off the road or does something wrong, and the human takes over by grabbing the wheel, and the robot gets some sort of feedback that is doing the right thing, or corrective feedback. The problem with this strategy, this feedback loop, is that it can be pretty greedy, in the sense that you may have to wait a very long time for this informative label, this correction. So a pessimist may say, an extreme pessimist may say, when Google says something like, the car has been on the road for over 100,000 hours without any human intervention. Pessimists may say, okay, so the car has been on the road for 100,000 hours and it's learned nothing. Right? Because it's got no informative labels. If you think about this as a discriminative classifier, it's discriminating, mapping states to actions, you're not actually getting any information on where this boundary is. You're just saying, you're doing great, car. And so what we need to do is we need to have these grand schemes, and people are starting to do this with simulated environment through video games and different ways of simulating different situations the car can get into so we can get these more informative labels more efficiently and quickly. But how do we choose these? And more serious of a problem with this type of algorithm, with this feedback loop, is that it can get stuck in local minima because the states that the car is realizing or visiting are based on its own policy. So if the policy is entering states based on its own policy and then getting feedback on those states, what can actually happen is you can shore up yourself in this local minima. You can be stuck in a local minima and become more and more confident that you're doing the right thing in that local minima. And so we showed this both theoretically and empirically in a robot arm that this can happen. And so trying to come up with techniques that can avoid this caustic feedback loop are a topic of great interest. So in my research going forward, my goal is to accelerate the rate of discovery with practical, sample-efficient, and reliable algorithms. And reliable, as I've been talking about in this talk, with reliability guarantees where we're going to get the same genes at the end of the day, or we're going to identify the best caption, or these sorts of things with some guarantee of success. And the way that I've done this, or tried to achieve this goal over the last several years and plan to going forward, is through a pipeline of sorts, where I work with collaborators like the New Yorker, like Google, like psychologists at Wisconsin and Berkeley, so that that are collecting lots of data on a weekly basis and trying out algorithms, getting stuff to work in that environment, so that when I have a more experimental prototype algorithm that maybe is the next NIPS paper or something, I have this environment already fostered, this collaboration, so that they trust me to inject something a little more crazy or experimental into the pipeline. But of course, where these algorithms come from, these prototypes, they come from theory, and they come from students. Because you need to know what you know to ask a good question. And this is quantifying uncertainty. So this is using tools from probability and statistics in order to quantify these sorts of things. And the point is here is that while on the implementation side of things, this requires coding and different more practical sort of skills, we also need a big theoretical background. And the point is that students can enter this pipeline at any point. Right? They can enter from the left and go right. I've worked with pure math students, and just on the theoretical side, and I've worked with students that, undergrads and first years on the implementation side, where they had their project and then they went off and did their own thing. That's fine. And so with that, I'd like to conclude, and thank you for your attention.
Pedro.
So the algorithm for adaptive parameter selection that you described seems very reminiscent of Hoeffling races.
Yeah.
What is the relation?
Yeah, so the question is, what is the relationship between the algorithm I described and Hoeffling races? So Hoeffling races is actually very similar to the successive elimination algorithm that I described in the first part of the talk. And the difference there is that Hoeffling races, from the name, are based on Hoeffling inequalities, based on bounds, confidence bounds. And the difference between Hoeffling races where you have these confidence bounds, here we don't. We don't know how quickly these sequences converge to their end value. And so the difference is that while Hoeffling races is totally applicable to the caption contest, it can't be applied to these more hyperparameter tuning problems because we don't know how quickly these things converge. And so the algorithm
has been applied to hyperparameter selection.
They have.
It doesn't have to be Hoeffling bounds, right? It can be whatever bound.
Yes. So how do we come up with these different bounds? What has been done in the recent research has been, and the past, has been two different approaches. One approach tries to learn these, extrapolate these learning curves, and tries to learn these uncertainties. And while this approach has been shown to work on a finite number of data sets, of course, it can't possibly generalize, right? I can come up with adversarial settings, of course, but of course these pursuits should be explored. The difference, though, the reason why I don't like these approaches is that they turn a optimization problem into a regression problem, right? Which is strictly harder. And so what I appeal to is more algorithms that are going after using a relative approach to killing these different alternatives off, where we don't need to suffer not knowing the convergence rates, but still get these sample complexity guarantees.
So a lot of the hyperparameters in deep neural networks are continuous, and you can't just make like one choice. And they can also be sort of infinite, where you could go up as high as you want. How are you dealing with those kind of hyperparameters?
Yeah. So the way the analysis works and the way that these algorithms work is I just need to have some protocol or some ability to sample from some distribution over this hyperparameter space. Okay? So it's not restrictive in any way as long as you can define any distribution you want over this hyperparameter space. And then the guarantees, of course, of how well this works will depend on how well you've defined your prior distribution that you've sampled from. And when I say randomly selecting these hyperparameters from some space, I don't necessarily mean a uniform at random allocation. If you have any sort of prior data that you can use as meta-knowledge to inform these priors to sample from, you should absolutely do that. And that is what's done in practice, is you don't need to have a uniform prior or anything like this. And so you should absolutely use any kind of side knowledge you have access to. But for the theory, we just sample from a distribution, and the algorithm works as well as that distribution is that you define.
I had a question about taking a question about this assumption of picking a random point and how well it does. So this is like this beta or something. why do we have any intuition for why a random, I mean, under any distribution, how well it's going to do compared to optima, whether it's a polynomial or any kind of.
Yeah, okay, you got me there. I was for that explicitly assuming that the distribution that you're sampling from is lower bounded by something everywhere, and so it kind of looks uniform, and then making this Taylor series assumption that it is smooth at the minimum, say, so that you could do a quadratic fit or something like this.
It's fine, but this sort of, this uniform.
Right. So I could say something like, but Sham, that's just, it'll take a finite amount of time to get down to that minimum, though. But in everything else, it's just constant factors. But in reality, yeah, it's a huge problem. And in practice, what you'd want to actually do is adapt these distributions over time. So I opened up by saying that if you do random selection, there's no way, and you do full evaluations, there's no way you're going to be able to cover this space. The hyperparameter space is just too large. But when you do this aggressive downsampling, when you are sampling at a small fraction of what you were sampling at before or training to before, you are getting many more coverage, right? The number of hyperparameters you get to look at is much larger, but just for a much smaller amount of time. And what you'd want to do is be able to use some sort of spatial adaptivity on those stages, because now you're actually getting to the point where you might be able to cover the space and learn something at least locally. So these are obvious pursuits of future work. But the tricky part there is to try to come up with a scheme that is robust enough to not make any strong assumptions, trying to learn some kernel or something like this, and also being practical enough to work in practice. And what I mean by that is you don't want to, it's very tempting to do something more spatially adaptive and more complicated, but often what can happen is you can shoot yourself in the foot trying to do something more complicated when the simplest thing would actually work better in practice anyways.
Suppose we are in a setting like, let's say, adversarial training, where you are given a distribution and you want to maximize for the worst case in that particular set. So can your algorithms be adapted to that setting where you want to maximize the worst case performance in some given models?
So I'm not sure I completely understand the question, but I can say that the algorithm is robust to oblivious adversaries, in the sense that the sequence of losses just need to be sort of fixed before the start of the game, but can be adversarial in that sense. But we cannot adapt to sequences changing over time. If they're adapting to what my algorithm is doing, we don't have any results on that. Does that answer your question? Okay.
Yeah, in the back.
So again, asking a follow-up question about hyperband, your hyperparameter optimization algorithm. In the paper that I looked up, I found a related work section in which you mentioned other algorithms that also have some early stopping.
Yes.
And primarily it seems like you say they make stronger assumptions, they make different assumptions which aren't verifiable. But I don't see if you compare your algorithm with them, and I'm just wondering if you have any evidence that how your algorithm would compare to, for example, like freeze thaw Bayesian optimization or some of the other ones that you mentioned.
Yeah. Okay. So as you pointed out, there have been many algorithms that have been applied over the last, or tried out, or proposed in the last several years. Things that, like Pedro was saying, there's algorithms that try to use confidence intervals. They try to learn the extrapolated curves like freeze thaw. And they've been used in the past to some success. How do we compare to them? Because you saw no plots today comparing to them. That's true. And in that paper, we also do not compare to them. So what we do in that paper is compare to the state-of-the-art Bayesian optimization algorithms for full evaluations. And that was a different work than what I was really focusing on today, where it's a more parallel environment where you get one evaluation. We have an upcoming NIPS paper where we do compare to freeze thaw in the more recent iteration Fabulous out of Frank Hutter's group that does aggressive downsampling, but then also has a spatial adaptivity. And so that's, I guess what I'm saying is stay tuned.
So you give the example of, say, car, right, where you're trying to learn from demonstrations and you might not get useful labels for a long time. But many of those potentially intermittent labels might also lead to, catastrophic results. Like you might have to actually crash to get something, such a label, which is in some sense like some constraints on your hyperparameters, but not exactly. There might be So how would you adapt to this type of setting, right, where you actually have these constraints?
It's a great question. Safe optimization is a major challenge going forward. Andreas Krause has actually done some excellent work in this recently in trying how do you optimize with respect to safety constraints or dangerous zones. And one of the challenges in this area is often you have stochastic constraints. You don't have hard constraints because you don't know what's safe and what's not safe. And you're just observing these signals, and you're trying to make sense of these signals and what constitutes safe versus unsafe, and trying to learn this over time. I think this is a great question, and I have nothing for you other than that. But there are fortunately people working on just this problem.
Okay, so let's thank Kevin, and if people have more questions, come up after.